Hey guys, it's Sharon with another coding interview tutorial. This one has been requested by subscribers, so thanks for the suggestion. I think it's a really good one, so I hope you enjoy it. Now this question is called pairs of songs with total duration divisible by 60, and the description goes like this. You are given a list of songs where the ith song has a duration of time at I seconds. We want to return the number of pairs of songs for which their total duration in seconds is divisible by 60. So formally, we want the number of indices I and j such that I is less than j with time at I plus time at j mod 60 equals 0. So if you're not familiar with this mod operation, this percent sign here, all it does is return the remainder of a division. So if it returns 0, it means that the division of this sum by 60 leaves 0 remainder, which means this sum is a multiple of 60. Now if you look at the first example, we get this array of integers. The output for this array should be 3 because there are 3 pairs of numbers that add up to a multiple of 60. This one adds up to 180, this one adds up to 120, and this one to 60. So that's 3 pairs. Now in the second example, the output should also be 3 because all 3 possible pairs add up to 120, which is of course a multiple of 60. Okay, so let's first solve this as naively as possible and go from there. So in this example, we would start with the first element and check its sum with all the others, right? And then we would move on to the second element and check its sum with all the others as well. And then the third, and we're done. So the first pair is going to be 20 plus 40, which is 60. 60 mod 60 is 0, which satisfies this condition. So we increment the counter and move on. The second pair is 20 plus 150, which is 170. Mod 60 is 50, not 0, so we move on without incrementing any counter. 20 plus 100 is 120. Mod 60 is 0, so we increment the counter. 120 mod 60 is 10. 140 mod 60 is 20. And lastly, 250 mod 60 is 10. So in total, we counted 2 pairs that satisfy the condition. So our return value should be 2, which is the correct answer. Now this algorithm translates very easily into code. We would just iterate over the pairs like this. Just a couple for loops. Now this j should actually start from I plus 1 because if we already counted this pair, we don't want to also count this pair, right? So this is why we need to start from I plus 1 so we don't count duplicate pairs. Now if the sum of the pair mod 60 is equal to 0, we want to increment some kind of counter, right? We also, of course, want to initialize this counter and, of course, return it. Okay, so this will do the job, but the problem is that the time complexity is going to be O of n squared because of these nested loops here, right? So, of course, we're going to want to optimize it, but before we do, I want to make our lives a bit simpler. So notice that this 60 here seems like a pretty arbitrary choice from the author of this question. I mean, I can't really think of anything special about the number 60, right? So I bet if we solve it for a smaller number like 4, the solution will still apply to the original 60. It's just so much easier to think of examples and visualize operations on smaller numbers. So let's just replace it with 4s for the time being. And the second change that I want to make is just give these guys names because I don't want to have to say time at I and time at j all the time, okay? So let me just call this guy X. And I'll call this one Y. Okay, so what exactly is this code doing? We loop over each element X, and then in this inner loop, we search for good matches for X, right? So if X plus Y mod 4 is 0, we say that Y is a good match for X and we increment the counter. Now we're not going to be able to get rid of this outer loop because we are always going to have to look at each element at least once, right? But we would like to replace this inner loop with something more efficient. Now this loop is performing a search on an array, and we know that searching a hash table instead of an array is going to be much faster, right? So what if we kept a hash table that had all the values we've seen already and then searched that table instead of the array? So in this example, at the point where X is 7, we've seen these values already, so they'll be in the table with their count. Now, searching this table will take average constant time, which is awesome. But what exactly are we searching for? if x is 7, do we search for 1 or for 5 or any of the other infinite possibilities that would make a good match for 7? It's clear that we need to reduce the number of possibilities. For each number x, we want to search for one number only. So let's look more closely at this line. Now in general, this mod 4 operation has only 4 possible output values: 0, 1, 2, and 3, because these are the only possible remainders when dividing a number by 4. We can think of this operation as a cycle. For example, to compute 3 plus 2 mod 4, which is 5 mod 4, we can take 5 steps: 1, 2, 3, 4, 5. Now we landed on 1 because after one full cycle, we had one more step left. And this is exactly the definition of a remainder, right? How many steps we have left that do not add up to a full cycle. In this case, we had 1. So wherever we land on this cycle would be the remainder. If we want to satisfy this condition, we would want to land on 0. Now let's think about the individual components x and y. Let's say that after x steps, we landed on 1. In this case, x could have been 1 or 5 or whichever number x such that x mod 4 is 1. Now if we want to get back to 0 at this point, we would need y to complete the cycle for us. So y could be 3, right? After 3 more steps, we're back at 0. But now that we're here, we can also take another 4 steps and another 4 steps and any multiple of 4 steps. So basically we don't care how many full cycles y makes, we only care about this number, the remainder. So if x mod 4 is 1, we would have to pair it with y such that y mod 4 is 3. 3 plus 1 is 4, which is a full cycle, and it ensures we do not have any extra remaining steps, meaning 0 remainder. In the same way, if x mod 4 is 2, y mod 4 would have to be 2, and if x mod 4 is 3, y mod 4 would have to be 1. So the more general rule would be that the sum of remainders has to be 4. One special case is when x mod 4 is 0. It's a bit different because we're already on 0 and we don't need y to compensate. We want to stay exactly where we are, so y mod 4 should be 0 as well. So now that we have these two rules, we can think of the algorithm. We know now that we make matches based on remainders only. The numbers themselves do not matter. So instead of keeping a hash table that keeps track of the count of the numbers themselves, we can track the count of remainders that we've seen so far. So at this point where x is 7, we will have these key value pairs in the table because we've seen one number with remainder 0 and two numbers with remainder 1. The remainder of x is 3, so based on this first rule, we know that good matches for x would have remainder 1. So we look for this key in the table and find that so far we have seen two numbers with remainder 1. It means that we found two good pairs, so we add them to the counter. Now we also add the remainder of x to the table before moving on to the next element. So our x is now 4, the remainder of 4 is 0. Based on the second rule, good matches would have remainder 0 as well. So we check the table to find how many numbers with remainder 0 we've seen so far. We've seen 1, so we add 1 to the counter, and of course we increment the count of the current remainder in the table. Our last element is 1, its remainder is 1, so good matches would have remainder 3. We search 3 in the table and see that we have seen one number with remainder 3, so we add 1 to the counter. And with no more elements to go, we are done, and our output is 4, which is the correct answer. Now notice that we can easily swap these 4s back to the original 60 and the solution will still hold. We didn't rely on anything specific to the number 4, so any other integer will work just fine. Now I think we're ready to write the code, so let's do that. In the algorithm we had a hash table called rem to count that would map remainders to their count, but because there are only 60 possible remainders, 60 possible keys to this table, we can actually just use an array. So this could be a vector of ints of size 60, and then I want to initialize it to 0 because these are the counts, right? Now let's get rid of this inner loop because that's the part that we replaced with the hash table lookup. And what we want to do is for each element x, we want to compute its remainder. Now based on the rules, if x has a remainder of 0, good matches for x would have remainder 0 as well. So we look at the table at index 0, and that is what we want to add to our count. And then for all the other cases, good matches for x would have remainder that adds up to 60. So for all the other cases, we want to add to the count everything that we have in rem to count 60 minus rem. And then of course, either way, we want to increment the counter of the current remainder. Okay, so that should work. The time complexity of the solution is going to be O of n, because for each of the n elements, we perform a constant amount of operations. And then the space complexity is going to be O of 1, because the only extra space that we're allocating is this vector, and its size is 60, which is a small constant. So we can say that the space complexity is constant. Okay, so let's try to submit this. Okay, so that's a success and we are done with this one. If you have any questions or requests, please post them in the comment section. And if you enjoyed this video, don't forget to like and subscribe. Thank you for watching and I will see you next time.